Hi everyone, my name is Allison Taylor, and today I'm going to be presenting on Physics 2212, Lab 5, Magnetic Braking with Faraday. So the objectives and introduction. So first we had to collect observational data of a magnet falling through a handcrafted aluminum tube. We used aluminum foil and bent it around to where it would create a tube-like structure. Second was to model the magnetic tube interaction computationally through GlowScript, as well as compare your computational predictions to that of your observed data. As you can see on the right, I've included Faraday's law and Lenz's law. This will be extremely useful throughout the experiment and require an EMF as well as flux and the derivative of flux with respect to time. Newton's second law of motion is listed below it and relies on the velocity parameters as well as the time difference. And the Biot-Savart law gives us data which tells us more about the magnetic field. So the procedure for this lab was to employ the app we used in Lab 3 to identify the north end of a magnet, construct a tube made from aluminum foil, hold the tube and drop the magnet through it, recording from your smartphone, which I propped my smartphone up and then had to hold the tube with one hand and magnet with another to ensure that the bottom of the tube was not touching or sitting on a surface. Number 4 was to identify the timestamps and magnet data, and number 5 was to run multiple trials to collect an average time. As you can see, I've listed my parameters below, the most important being an average time of 0.862 seconds, and my magnet had a magnetic dipole moment of 2.93 joules per Tesla, as I identified in Lab 3. So here is an example of some snippets of my GlowScript code. Box 1 shows the initial values I measured, box 2 being the information from Lab 3 about the magnet and the mu value. Box 3 talks about the formula for a magnetic field using the while loop that we've discussed previously. In box 4, I'm getting the derivative of flux through the rings, each ring due to the magnet. Number 5 is going to be where the Biot-Savart law comes into play, as we're looking at the force exerted on each ring. And box 6 displays the net force in Newton's second law. So here's a snippet of the model I've produced. As you can see, I have created a tube with a model magnet going through it at a time of 0.372 seconds, and I have my velocity versus time data mapped off to the right. So just a little bit of interpretation based off the questions prompted in the lab. My total time in the tube versus real world were a little bit different, and I think that that's because GlowScript did not account for the air resistance, and maybe why my real life time measurement was higher. So it was 0.8 seconds in real life and 0.32 seconds via GlowScript. The shape of the velocity versus time plot tells us that the magnetic force and gravity, force from gravity, reach a point of equal and opposite magnitude. This is where the velocity is constant, and that's represented by a horizontal line on that previous graph. Some of the additional questions asked at the bottom of the lab were, what if the resistivity of the conductor were reduced as close to possible to 0? This would mean that the induced current would increase, so the magnet would fall through the tube much slower. And if holes or slots were cut into the tube, the magnet would fall through the tube more quickly because there would be less induced current, and so it would fall faster. We did a few things throughout this lab. We created GlowScript code and a model to represent various parameters related to Faraday's law, interpreted and compared computational data to real-life surroundings, as well as applied physics principles to a real-life scenario that has applications in various industries today. Thank you.